This is part 1 of a series of lessons dealing with the quantum mechanical description of molecules. When dealing with molecules, as with any multi-particle system, it is convenient to think of the total energy as a sum of the translational energy, which is the kinetic energy associated with the motion of the entire molecule as tracked at the molecule's center of mass, and the internal energy, which is associated with the motion and interactions of the nuclei and electrons relative to one another. The time-independent Schrödinger equation that we need to solve to describe translational motion, H hat psi trans equals E trans times psi trans, is essentially a free particle or a particle in a really large three-dimensional box problem. Translational energy is essentially continuous. The Hamiltonian for the translational motion is the sum of the kinetic energy operators due to motion along the x, y, and z axes. In this expression, uppercase M is the total mass of all the particles, and the uppercase letters x, y, and z represent the Cartesian coordinates for the center of mass. The problem is essentially the same for all molecules except for the total mass m. And we already know the solution. So, for the rest of this lesson we will focus on the internal or relative energy. From here on, since we're not interested in the center of mass coordinates anymore, we will simply just say coordinates instead of relative coordinates or internal coordinates. We will also simply refer to the part of the Hamiltonian operator that depends on the internal or relative coordinates as h hat. H hat is a sum of the kinetic energy operator for the relative motion of the nuclei, T sub n hat, the potential energy due to Coulombic repulsions between each pair of nuclei, V sub n hat, the kinetic energy of the electrons, T sub e hat, the potential energy due to attractions between each possible electron nucleus pair, V sub e n hat, and the potential energy of repulsions between each pair of electrons, V sub e hat. The sum of the last three terms is called the electronic Hamiltonian. In the Born-Oppenheimer approximation, we fixed the coordinates of the nuclei, which we can collectively represent by the symbol q sub n. Then we solved this simplified Schrödinger equation, which is called the electronic Schrödinger equation. In other words, we imagine fixed locations for all the nuclei, then solve for the eigenfunctions and eigenvalues of the electronic Hamiltonian. The wave functions we get depend on the coordinates of the electrons, which we can collectively represent by the symbol q sub e. But the dependence on the electronic coordinates depends on the coordinates we choose for the nuclei. We say that the wave functions depend on electronic coordinates and, parametrically, on nuclear coordinates. We represent this idea mathematically by putting a semicolon before q sub n instead of a comma in the expression that says that psi depends on q sub e and q sub n. The corresponding eigenvalues also depend on the nuclear coordinates that we choose. By solving the electronic Schrödinger equation at different sets of nuclear coordinates, we get a function called the molecular potential energy. The molecular potential energy, often represented by uppercase U, is the sum of the eigenvalue of the electronic Hamiltonian and the potential energy due to repulsions among the nuclei, both of which depend on the nuclear coordinates that we choose. Shown here are the molecular potential energy functions for the simplest possible molecule, H2+, which consists of 2 hydrogen nuclei and 1 electron. For diatomic molecules like H2+, the molecular potential energy depends only on the distance, r, between the nuclei. The energy scale for the curves shown here is given in atomic units or hartrees. 1 hartree, or 1 atomic unit of energy, corresponds to 2 times the Rydberg constant, or 27.2 electron volts. The distance scale for the curves shown here is given in atomic units as well. 1 atomic unit of distance, or 1 Bohr, is equivalent to 52.9 picometers. Since we get a set of eigenvalues for the electronic Hamiltonian for a given r, we get a series of potential energy curves. We say that each curve corresponds to an electronic state. In the figure here, the red curve labeled as 1 sigma traces the lowest values for the molecular potential energy. So this curve represents the ground electronic state of H2+. The first excited electronic state is the green curve labeled as 2 sigma. Every point on every curve represents a solution to the electronic Schrödinger equation. For example, if we were to set the value of R equal to 4 Bohr, then this point corresponds to the electronic wave function with the lowest eigenvalue. This is the ground electronic state at R equals 4. The molecular potential energy at this point is equal to the eigenvalue plus the potential energy due to repulsion between the two nuclei. This point corresponds to the first excited electronic state at R equals 4. Since the wave functions, in this particular case, depend on the coordinates of only one electron, we call these functions molecular orbitals, just like we use the term atomic orbitals for atomic wave functions that depend on only one electron. Just like we did for atoms, we will use orbitals to construct wave functions for molecules with more than one electron. Let's go back to our Hamiltonian for the internal motion. Recall that we defined the electronic Hamiltonian as the sum of the operators that depend on electronic coordinates. By applying the Born-Oppenheimer approximation, we are able to calculate the molecular potential energy function, which depends only on the nuclear coordinates, but accounts for electronic energy and the potential energy due to repulsions among the nuclei. We get a series of molecular potential functions and we associate each of these functions with an electronic state of the molecule. Now, the next step is to replace the nuclear repulsion and the electronic Hamiltonian by the molecular potential energy function. This gives us a simplified expression for the Hamiltonian for internal motion. Note that this operator now depends only on the nuclear coordinates. So, now, we can solve a simplified Schrödinger equation to describe the relative motion of the nuclei for a given electronic state. The wave function depends only on the nuclear coordinates, so the solution gives us a description of the nuclear motion only. But, keep in mind that the molecular potential energy function does account for the overall effect of the electrons on the wave function that describes the nuclei, as well as the energy of the molecule. Note that E here does not include translational energy. We need to add the translational energy to this if we want the total energy. For a given electronic state, the symbol T sub E is typically used to represent the minimum value of U. It is customary to refer to T sub E as the electronic energy for that state. We associate low potential energy with stability. So, the minimum value of U is associated with what is called the equilibrium geometry of the molecule. Note that although T sub E is called the electronic energy, it is in fact a sum of the eigenvalue obtained by solving the electronic Schrödinger equation and the potential energy due to internuclear repulsions at the equilibrium geometry. For diatomic molecules, the molecular geometry is defined by specifying the distance, r, between the nuclei. And the symbol R sub E is typically used to represent the equilibrium internuclear distance. So, for a given electronic state of a diatomic molecule, T sub E is the value of the corresponding molecular potential energy at R equals R sub E. The total internal energy of a molecule is a sum of T sub E and contributions due to motions of the nuclei, which can be thought of as vibrations and rotations. Uppercase letters G and F are typically used to represent vibrational and rotational energies, respectively. Let's examine the typical molecular potential energy functions that describe electronic states of diatomic molecules. For a diatomic molecule, the potential energy function approaches a constant value as the internuclear separation, R, approaches infinity. This constant value is just the electronic energy of the separated atoms. For example, in the case of H2+, the potential energy for the two lowest electronic states approaches the value of the electronic energy associated with a hydrogen atom with an electron in the 1s orbital, which is negative 1/2 Hartree. Since an H2+ molecule ion consists of two nuclei and one electron, we can imagine that R equals infinity corresponds to a situation where we have a hydrogen atom and an H+ ion at infinite distance from each other. The electronic energy is just the electronic energy of the neutral H atom. for this set of excited electronic states. At very large internuclear separation, the potential energy functions approach the electronic energy associated with a hydrogen atom where the electron is either in the 2s or a 2p orbital, which is 1/8 of a Hartree. At very short distances, the potential energy function essentially approaches infinity due to very strong repulsions between the nuclei. Note that at internuclear separations very close to zero, our formula for the potential energy of interaction of the two nuclei is no longer correct. The interaction is not just Coulombic anymore. We have to take into account nuclear forces as well. When the two nuclei of H2+ merge into just one nucleus, we end up getting a helium nucleus. We say that the united atom limit for H2+ is a helium ion with a charge of +1. And the electronic energy will just be the electronic energy of this hydrogenic ion. Thankfully, for chemistry applications, we don't have to worry about this case. We're only interested in distances for bond breaking and bond formation. That would be from at least the typical bond lengths in molecules, about 1 to 2 angstroms. We just saw that the molecular potential energy curve, for a diatomic molecule, levels off at very large internuclear separation. The large distance limit, U at infinity, is just the sum of the electronic energies of the separated atoms. As the internuclear separation becomes very small, the potential energy rises steeply due to strong internuclear repulsions. What else does a potential energy function tell us? Depending on the electronic state, it is possible for the molecular potential energy to dip below the value of U at infinite separation, as shown here. The dip can be mainly attributed to attractions between the nuclei and the electrons. As mentioned earlier, the distance where the molecular potential is at a minimum is called the equilibrium internuclear distance and is typically referred to as R sub E. In the example here, R sub E is about 75 picometers. And the value of the molecular potential at R sub E is referred to as the electronic energy, T sub E. The electronic state is said to have bound states when the total internal energy is between T sub E and U at infinity. For example, consider a molecule whose total internal energy is given by the dashed line in the figure. Classically, this is the closest allowed distance between the nuclei. Shorter distances are classically forbidden since those would correspond to total energies less than the potential energy. Similarly, this would be the farthest they can be from each other. Longer distances are classically forbidden. Of course, quantum mechanics says that there is a finite, but very low probability of the distances to be in the classically forbidden regions. But for the most part, the distance between the nuclei will be within the classical limits. Because of the shape of the potential energy function, the two atoms can be described as being trapped in a potential well. The depth of the well is called the classical dissociation energy, D sub E. Recall that dissociation means atoms moving as far apart as possible. Here, we can see that D sub E is the difference between the U at infinite separation and the U at the equilibrium internuclear distance. If the difference between the total energy and T sub E is equal to D sub E, then the atoms have just enough energy to move as far apart as they can. If the difference between the total energy and T sub E is larger than D sub E, then the atoms have more than enough energy to separate. The wave function for nuclear motion is not normalizable. Energy is not quantized. And the states are called continuum or free states. Consider the electronic states represented by the potential energy curves shown here. The blue curve dips below the potential energy at infinite separation. Based on the preceding discussion, we can say that the electronic state represented by this curve has both bound and continuum or free states. The energy of the bound states are less than U at infinity. And the energy of the free states are greater than U at infinity. Now consider the orange curve. We can see that the potential energy is greater than U at infinity for all values of R. This means that the allowed energies are all greater than U at infinity. In this case, we can only have free states. We can describe the electronic state and the potential energy curve as completely repulsive. the atoms will not form a stable bond. Consider the total energy indicated by the dashed line. Does this energy correspond to a bound state or a free state? Let's see. Regardless of the electronic state, the energy is higher than U at infinity. So this energy level corresponds to a free state. The atoms would not form a stable bond if they have this much energy. For a diatomic molecule, the simplified Schrödinger equation for nuclear motion is essentially that of a two-particle problem. This means that we use the reduced mass of the two nuclei in our expression for the kinetic energy operator. Since the potential energy function depends only on the distance between the nuclei, we have a central force problem. This means that the wave function for the relative motion of the nuclei can be written as a product of a function of r and a spherical harmonic. The total internal energy is equal to the electronic energy T sub E plus the vibrational energy G plus the rotational energy F. T sub E is the molecular potential energy at the equilibrium internuclear distance R sub E. At internuclear distances close to R sub E, the molecular potential energy function resembles a harmonic oscillator. U is approximately equal to T sub E plus 1/2 times K times the square of R minus R sub E, where K is the force constant. So, the vibrational energy G is approximately equal to V plus 1/2 times h nu, where the quantum number V is restricted to non-negative integers. The rotational energy can be approximated by the rigid rotor formula, B times J plus 1, where B is the rotational constant, and quantum number J is a non-negative integer. The figure shown here illustrates the typical difference between the correct molecular potential energy curve for a diatomic molecule and the potential energy curve for a harmonic oscillator that agrees with it at low energies. Here, the orange curve is the correct molecular potential energy curve and the blue curve is the harmonic oscillator potential. Vibrational energies are often expressed in reciprocal centimeters instead of joules. In these cases, omega E is used in the formula instead of h nu. So, you may see the formula for harmonic oscillator energies as omega E times V plus 1/2. As you have previously learned, allowed energy levels for a harmonic oscillator are equally spaced. Gaps between adjacent energy levels are equal to h nu, or omega E. However, we can see from the figure here that the molecular potential energy curve deviates from the harmonic potential at higher energies. It is steeper at shorter internuclear distances. Here's the equilibrium internuclear distance, R sub E. To the left, we see that the orange curve is steeper than the blue curve. Moreover, the molecular potential energy curve is significantly less steep at distances larger than R sub E. In fact, the curve eventually becomes horizontal when the atoms become very far apart. This deviation from the harmonic model is called anharmonicity. A consequence of anharmonicity is that the gaps between allowed energy levels decrease at higher energy levels. As a matter of convenience, the vibrational energies are expressed as a harmonic oscillator energy plus correction terms that involve powers of V plus 1/2 in order to account for anharmonicity. The constants omega E xe, omega Ey, and omega Eze are called vibrational constants. The formula for rigid rotor energies is a good starting point for approximating the allowed rotational energies of a diatomic molecule. Recall that the allowed energies are given by rotational constant B times J plus 1, where the quantum number J is a non-negative integer. Assuming the molecule is a rigid rotor, B is equal to B sub E, which is equal to h bar squared over 2 times I, where the moment of inertia, I, is equal to the reduced mass times the square of the equilibrium internuclear distance R sub E. Here, we are assuming that the distance between the nuclei is fixed and equal to R sub E. For better accuracy, we have to account for molecular vibration. Because of anharmonicity, we expect the average distance between the two nuclei to be larger than R sub e. And it gets larger for higher vibrational energies. If we were to plug in the average distance instead of R sub e in the expression for B, then we can expect an effective rotational constant that is smaller than B sub e. This also means a lower rotational energy F for a given J. We represent the effective rotational constant with B sub V. The correction terms added to B sub e to get B sub V are typically written as a polynomial in V plus a half. In the expression given here, V is the vibrational quantum number. And B sub e, alpha sub e and gamma sub e are called rotational constants. There is one additional correction we need to make, and it's called centrifugal distortion. Centrifugal distortion refers to the lengthening of the bond due to rotation. Again, this effectively lowers B and lowers F for a given J. To account for centrifugal distortion, we subtract d sub e times the square of J times J plus 1. The rotational constant d sub e is very small, so the correction becomes significant only at very large values of J. Please note that this d sub e is not the same as the classical dissociation energy you saw earlier. So, be mindful of the context when looking up literature values for d sub e. An extensive compilation of electronic, vibrational, and rotational constants for diatomic molecules based on experimental spectra can be found in a monograph by Nobel Prize winner Gerhard Herzberg. The compilation is now available on the NIST Chemistry webbook. It should be easy to search for the website. Using a smartphone, you can get to the search page on the website by scanning the QR code shown here. When this video was created, this is what the search page looks like. Simply enter the formula of the molecule. And check the box for constants of diatomic molecules. Then click the search button. Here's what you'll find if you do a search for the I2 molecule. If you scroll to the bottom of the table, you will find the molecular constants for the ground electronic state. Don't scroll all the way to the bottom of the page since a long list of citations to the primary literature is given below the table. The leftmost column gives the name of the electronic state. By convention, the ground electronic state is called the X state. Additional information about the electronic wave functions are also given as part of the name. For I2, the X state is a singlet sigma G+. We'll talk more about what this means later. The value of T sub E is in the second column. By convention, a T sub E value of 0 is assigned for the ground electronic state. Quantum calculations will give you a negative value for T sub E of the ground electronic state. But don't worry. Remember that the potential energy scale is not absolute. For comparison with the experimental values tabulated here, simply add a constant offset to the calculated potential energy functions for all electronic states so that the calculated ground state T sub E is 0. The third, fourth, and fifth columns give the vibrational constants omega E xe, and omega E ye. If you see a blank for any of these, you can assume the value is 0 based on currently available information. The blue text are hyperlinked to a footnote below the table, which may include additional information. For some molecules, for example, values of omega Eze for a particular electronic state might be given in a footnote. The next 5 columns give the rotational constants, B sub E, alpha sub E, gamma sub E, D sub E, and beta sub E. Beta sub E allows us to correct for the effective vibration on the centrifugal distortion in the same way that we use alpha sub E to make a correction to B sub E. There is also a column for the equilibrium internuclear distance, R sub E, which is somewhat redundant since you can calculate it from B sub E. Names of electronic states of diatomic molecules consist of a letter plus additional codes. Here's a partial screenshot of Herzberg's table for diatomic sodium molecule. As mentioned earlier, the ground electronic state is assigned the letter X. Letters for excited states are assigned alphabetically in order of increasing T sub E values. With a few exceptions, uppercase letters are used for states that have the same multiplicity as the ground state. Lowercase letters are used for states that have a different multiplicity. For diatomic sodium, the ground state is its singlet sigma G+. It's a singlet state. Notice that the excited state assigned to uppercase A is a singlet sigma U+. Uppercase B and C are assigned to singlet pi U states. But lowercase a is assigned to this triplet pi state. Uppercase Greek letters sigma, pi, delta, and phi are codes for quantum number lambda, which gives us information about the component of the electronic orbital angular momentum along the internuclear axis. Sigma means lambda equals 0. Pi means lambda equals 1. Delta means lambda equals 2. The internuclear axis is taken as the z-axis, and the z component of the total electronic orbital angular momentum is either positive lambda h bar or negative lambda h bar. Earlier, we saw that the X state of diatomic sodium is its singlet sigma G+, and the A state is its singlet sigma U+. What do the labels G and U in the name mean? These labels are only applicable to electronic states of homonuclear diatomic molecules. They tell us about the symmetry of the function with respect to inversion. Inversion means applying the parity operator on the electronic wave function. This means replacing coordinate x by negative x, replacing y by negative y, and z by negative z. If we get back the same wave function, then the electronic state is said to be symmetric and is designated as Garrod. If we get back the negative of the wave function, then the electronic state is said to be antisymmetric and is designated as ungarrod. How about the plus or minus labels written as superscripts? They tell us whether the wave function for a sigma state is symmetric or antisymmetric with respect to reflection through a vertical plane. A vertical plane, also called a sigma v-plane, is one that contains the z-axis. For example, reflecting through the xz plane means replacing coordinate y by negative y. A plus label means that the reflection does not change the wave function. The wave function is symmetric with respect to reflection. A minus label means that the wave function is antisymmetric with respect to reflection. This is all for now. In future lessons, we will learn how molecular constants for calculating the energies of a diatomic molecule are obtained from experimental spectra. We will learn how to calculate and visualize electronic wave functions using computational chemistry software. And we will extend the lesson to polyatomic molecules.